My name is Rose. I am a product manager in Google Cloud TPU team. And today I'm going to focus on talking about TPUs for large-scale training and inference. And very excited to be here. So feel free to ask questions and make it interactive. So just want to start the presentation by looking at the AI infrastructure landscape, right? Looking at the models, they have been growing tremendously from the model size, from contact length. We're looking at in 2028, millions of parameters. And now we're growing into hundreds of billions of parameters. And looking to next year, actually this year, 2025, we're seeing 1T model coming to the market with contact length at 1 million token contact length. So all these are basically requiring tremendous amount of compute, memory, networking. Just by doing simple math, we're looking at 10x growth per year in terms of the model size. And also looking at another dimension in terms of training, post-training, inferencing. There's mechanisms in terms of the hardware, software, specialized for pre-training scaling. There's definitely, like with lots of talks about this is the era of inference, a lot of the hardware innovations to enable cost-effective inference. And then with reasoning, end of last year, boom, DeepSeek, right? Lots of innovations about reasoning and this whole models around sampling is becoming a thing. Latency, on-chip latency, in-system latency, token latency is becoming very important in terms of model time to market, as well as the model quality. So all of these essentially triggered Google to focusing on our specialization for our TPU chip as well as the TPU system. In terms of our specialization, of course, the TPU chip by itself is our special designed, purposeful designed ASIC for machine learning applications. And we have generations of TPUs. I'll show you the roadmap in the later slides. Besides the purposeful built TPU itself, we also have innovations around power, around networking, around memory. So in terms of, essentially, we all know nowadays it's in terms of the machine learning accelerators, there's a big bottleneck at the data center space and the power. So from our perspective, we put a lot of effort to optimize the power design for our TPU platform. And in particular, we identified that there's a lot of power, actually, like up to 10% of the power got wasted at the PCB board level. So we're doing this particular vertical power delivery at the rack level to improve the power efficiency. This can prevent 70% of the power waste. And in terms of our power efficiency, we're looking at 70% power saving by doing the power delivery, vertical power delivery.
So just a quick question on the Andy Benta here. So by vertical power delivery, do you mean you're actually like powering the device directly without it going through the circuit board?
So it will be, but it's just from power direction-wise. We're choosing the Z direction to prevent some of the power waste. So it's still going through.
Okay.
Yeah. And then in terms of the networking, it's already our third generation to use our Jupyter network with the optical network. And there's optical mirrors to basically enable reconfigurable network and enable us to basically reconfigure the network to gearing towards better, to make it better for the workload. And also we have the ICI network. It's tremendously much faster than the Ethernet DCN. So if you think similarly, it's very similar to the NVLink from GPU side of the world. For our ICI, we've been using it from the early days of TPU development. So there's years of maturity for our ICI network. I'll show you the scaling of our ICI network, especially for our upcoming Ironwood. It is up to 9,000 plus chips to be in the single ICI domain. That's basically the biggest superpod. And in terms of the liquid cooling, again, for Ironwood, it will be our 4th generation of liquid cooling generation. So with liquid cooling, it basically provides us sustainable and consistent performance under this cooling system to provide better TDP and flops performance. And also in terms of our TPU, one of the secret sauce is it is not just the chip and it's not just the infrastructure platform. It is co-designed with our software. So the TPU itself, we're deploying in large scale, tens of thousands of TPUs interconnected together. And by itself, it is like a supercomputer working as one system. And then with the software stack, we enable JAX. JAX is Google's framework designed by for TPU, designed by our researchers. And also we support PyTorch, which has a much bigger ecosystem. And then from the framework, which is easy to use, enabled by the Python libraries, there is a low-level compiler. So TPU has the XLA, which is essentially generates the compilation graphs, and then it compiles once, execute many times. The compilation graphs takes more time, but once it's generated a graph, it will just execute to be able to work with the low-level hardware so that the sophisticated developers will be able to even better maximize the performance. And for some customers who are very sophisticated customers, they're able to even go down to the kernel using our Palace kernel programming to maximize the TPU performance and to achieve near roofline performance for TPU. So this co-design is very important. Essentially, our secret sauce is for TPU itself. It has the like relatively simple architecture where it for the Tensor core it is the multiplication with matrix plus the lots of HBM for memory, and then for the co-design we have the software to be able to help the hardware to maximize its performance.
That sparse matrix optimized also? Is that?
Yes, sparse core. So, so I think you're talking about the sparse core for embedding models, right?
Yeah.
So that's another part of the TPU where so Google has like YouTube ads. These applications, they sometimes their machine learning models require a lot of embedding model, and those are large data sets. And if you use traditional, say, CPU or general purpose GPU, that actually takes a long time to do the embedding exercise. With TPU, we have specialized sparse core. That's a particular hardware ASIC to enable much faster embedding execution. So for that, definitely through XLA, these are optimized, and whether it's for our, we call it 1P Google customers, which is basically our YouTube ads customers, search customers, or our external 3P Google Cloud customers, they're able to basically optimize for the TPU generations that has the sparse core ASIC.
So would you, Guy Currier at Futurum, so would you consider that an example of the co-design sparse matrix?
Yes, it's definitely.
Not exactly common, but you know, it's you know, appearing in a lot of places. But for that, because you gave two, you know, one first-person examples, seems that was a co-design vision.
Oh, yes.
earlier
yes.
on.
Yeah,
Oh, great.
definitely. Yeah.
Great.
And then just want to show you from TPU perspective, many people ask, hey, who's using TPU? Obviously, all of our Google internal machine learning applications, most of them are powered by TPU ever since 2018. So a lot of these well-known applications like Gmail, YouTube, they have billions of users across the worldwide. They're powered by TPU for the machine learning piece. And then for our cloud customers, we're also crossing different customer segments. So for example, like the ML unicorn, like Anthropic, they're a known TPU customer. They're using TPUs for their foundational model builds and for their applications for inference. And also we have enterprise customers like Salesforce, Mercedes, and we also have customers across, not just American customers. We have Korean customers like Kakao. So TPU has been, our customer base has been growing in all kinds of customer segments. And in terms of our TPU consumption, this metrics of chip per hour, within 12 months, we're seeing 8 times more growth to basically demonstrate the wide adoption of our cloud TPU. Okay, so Ironwood. This was one of the most exciting moments in April, Google Next, where our executives announced the TPU 7th generation, Ironwood. So it's coming soon. In terms of GA, it will be Q4 this year, 2025.
We were marveling that all of the early questions before you arrived were always, Rose will answer that. And so we're here.
Yes, please. Like it's as the product manager, right? We're so excited about Ironwood, and with the blog that was published by Amin, our VP. There's definitely a lot of comparisons for Ironwood, whether it's comparing with our prior TPU generations or with other platforms. So definitely I want to provide some metrics so that you can do some cross comparison. In terms of Ironwood, there are 2 configurations at the platform level. So the TPU7X, that is basically based on the 3D Taurus architecture, and from the superpod perspective, it will go to 9,216 chips per superpod. That is chip-to-chip, all interconnected through the fast-speed ICI connectivity. And then for TPU7, that is basically using the 2D Taurus architecture, so 256 chips per pod. We call it light pod. It's very similar to Trillium, the TPU system launched in 2024. The reason we do these 2 is, as I mentioned earlier, global-wise, there's a shortage for data center space and power. So in case there's data center that cannot fit in the liquid cooling system, doesn't have like space for 9,000 chips for superpod, then we can still fit in 256 chips in the light pod so that we can reach more regions to the customer. And also for certain in-country requirement, sovereignty requirement, or super low latency where customer need the compute to be close towards them. So the TPU7 actually provide more flexibility in terms of locality. So two configurations for the system. And then let's look at this slide, and then we can do some comparisons, right? So in terms of the chip spec, the Ironwood has BF16, FP8, and especially for FP8, this is where it's natively supported by the chip. So 4,614 T-flops. I think earlier there was a question about how does it compare with the first generation of TPU. So So with FP8 T-flops times the number of chips in a superpod compared to back then in Gen V1, where the chip, at that time there's no FP8, so we use emulated number, and then times the 256 chips per pod. At that time, that pod was 256. So with that comparison, that is 3,600 times difference from Ironwood to the first generation of TPU. And in terms of power, we also have some calculation. So from the power efficiency, we also use the FP8 flop per chip, and then use the per chip power. So by comparing Ironwood versus our V1, the ratio is 29 times power efficiency. Okay.
The ICI bit was so.
Yeah.
Help me unpack the chip specs. That's 600 unidirectional gigabytes per second.
Yeah. So gigabyte, that's basically if you want to convert to gigabit per second, then you need to times 8 for that.
And for the high bandwidth memory.
Yeah. So for the HBM, that is basically 7,380 gigabytes.
Okay, that's what I thought I saw.
Yeah.
All right.
Yep.
That's fast.
Yes, definitely. Thank you.
Okay. At first, I just assumed that was a decimal point there, but it's a comma, everyone.
Correct. And also for HBM, essentially nowadays with the LLM model, especially with the MOE models, a lot of the bottleneck is at HBM bandwidth.
Sure.
So this is where we put a lot of effort to make sure we stack the HBM horizontally, vertically, so that it can provide not just the HBM quantity, but also the bandwidth.
Is last level cache even a consideration here? Like cache, is that even a consideration with those kind of bandwidth? It's an ASIC also. I don't even know. Like, is this heavily cached or no?
So we do have the DRAM at the host where the customer can.
The HBM is a cache.
Yeah. So the customer can also do some sort of host offload. I'll have a slide later to show you, like you can also do some host DRAM offload to improve the performance as well.
Yeah, that's south band. That's south. I was talking about. Just go on.
Yeah. Okay.
Wow.
That's good. Yeah.
Okay.
And again, right, like as I mentioned earlier, that 3,600X compared to our V1, that is basically based on the 42.5 exaflops per superpod.
Now I know where that comes from. Okay.
The scale of this the superpod essentially enable the customer to run, we call it large hero jobs for training without very complex like parallelism, right? So because you can basically fit in your job in the large superpod.
Exactly.
And also beyond the superpod, we also we're already seeing customers in our 5th generation or 6th generation Trillium, where customers are connecting many pods together so that the largest training jobs are running on tens of thousands TPU chips.
What's the power draw for this per socket, or what's the power draw for it?
So it's about 1K for the TDP.
1,000 watts.
Yeah.
For one TPU?
Yeah.
For one chip. Yeah.
One chip.
One chip.
Yeah.
Yeah, one chip. Yeah. No, there's.
I think it's comparable to the other.
Yeah, the latest GPUs right now are around 1,000, but they're not doing. They're not really general purpose, but they're more general purpose.
Yeah.
So that's 1,000. Yeah. Okay. All right.
9,000 chips. So that's a nuclear central that you need.
And JQ Thrill, Nexus Tech, I'm supposed to say my name, and there's no Chiron to say that yet.
Submerged the whole.
But when you described, you've got all the engineering that's going into deterministic power, weight, cooling, geometry. Then there are the proprietary things that you were doing as Google, and if that's your prerogative to do those things. it does appear that you're also providing more runway for your existing real estate investments, the actual plate of the data centers that you already have. And so as you showed those generations, I'm also kind of wondering if I'm currently on a prior generation, when will I be encouraged to move to the 7th generation? And so how is the Google product team thinking through how do we bring customers forward to the 7th generation, knowing that they may be on much earlier generation? What's your thinking on there? Because it seems like it's a very advantaged position for you to roll out this latest and greatest as compared to. But how are you working with customers and possibly systems integrators, partners in the ecosystem that are Google partners? How are you guiding that conversation?
Yeah, definitely. So great question. For TPUs, right? As you can see, we have a busy roadmap, very promising roadmap. Almost every 12 to 18 months, we're coming with a new generation. And then global-wise, there is a shortage of accelerators. So proactively, our customers, like our existing customers, they're asking for whether it's more older generations as well as new generations. It's just not enough. So from our perspective, obviously, we want to enable our existing brownfield customers and greenfield customers to adopt new generations. So from our consumption model perspective, we have on-demand reservation. For reservation, we have 1 year cut, 3 year cut. Basically, the cut is the commitment, right? And even with 1 year cut, 3 year cut, now we're actually in preparation for the 2 year cuts as well, to basically enable customers to have more flexible consumption models.
Okay.
And then at the same time, we have customers who have been using our, say, like V5P, V5E, and they like it very much, and their engineers optimize their model, and they want to expand. They're asking more as well. So to be honest with you, the conversation is going different directions. And as product manager, as capacity planning team, this is one of our daily job to be very adaptive and versatile to go around the capacity planning and the deliverable and the strategy.
And as a specific follow-on question, so if we said Ironwood is coming Q4, and we're in Europe and we have a decision to make, are we saying Ironwood goes into, say, Frankfurt, or we go to Eemshaven, where the energy source is different?
Yes.
Is that where you work with capacity team?
Definitely.
Okay.
Yeah, great, very good question. So I'm so happy that you brought this up. Essentially for TPUs, in the past, especially with the liquid cooling system, it's in very few locations, right? But with the light pod, we're able to deploy it in more locations, and especially with the 6th generation Helium, we're able to actually working with 3P Colo to bring it to more locations. However, remember, these type of location with data center contract, this needs to happen many months beforehand, right? It's not like, say, in Q4, we are GAing the product, then customers say, hey, I want it to be in Frankfurt. Is it there? Is it not there? We need to know the signal. So it's basically demand and supply. We need to know the signal right now. And that's why from a product management perspective and our go-to-market team perspective, we're doing road shows. We're engaging with our known customers, beachhead customers, or greenfield customers to get in the signal so that we will be able to plan ahead of time. And in particular for Frankfurt.
And so a third follow-on question, if you'll allow. If there's a power purchasing agreement, a virtual power purchasing agreement, a PPA, VPPA, are you having to, again, plan in advance and work with the local regions, the governments, the utility providers? Because we're in the United States now, but there's a large world around us.
Yeah.
each country will probably have unique negotiations that you as a tenant of that country,
Yeah.
sovereign, otherwise. So is it fair to say that, yes, it's coming, but one of the reasons for TPU7 is so that you can be in more places more quickly? Not everything is going to be TPU7X immediately, but 7 allows you much faster time into market. Is that fair?
So in terms of the power data center, it is actually a very dedicated, there's a huge organization in Google specifically managing that.
Yeah.
And then they will basically allocate the location, the power to whether it's TPU7, TPU7X. And then with that, we'll be able to fit in our footprint into those data centers, right? We are actually also in the process to getting the customer signals in terms of how many TPU7X from demand perspective, how many TPU7 from demand perspective. To be honest with you, right now, both of them are high. So it's a good problem to have. And then internally, we just need to be very cautiously to distribute which one gets what.
Just one other quick comment. I know we're also short on time, but that power planning goes well beyond just the TPU because there are storage implications, networking, all the servers, everything is much broader, and obviously AI workloads.
All those prior
things.
optimizations, yeah.
Like it's a very complicated but very detailed process.
Okay, so here this is another graph where I want to show you, right? From TPU perspective, out of the box, we have the XLA, that's the compiler. So we expect XLA can bring the performance by 70% of the MFU. And then there are a couple of different ways to optimize the performance. So flash attention, that will basically, in this particular example, that basically bring the performance by 10% better performance. Then by doing the offload to host DRAM for activations, that bring another 10%. And then lastly, by using mixed precision training to do AQT with int8, that basically makes the performance to 1.6x compared to the initial out-of-the-box just by XLA optimization. So this gives an example of how sophisticated customers are able to improve the performance for TPU. And then GKE, actually for TPU, we have two ways of doing the orchestration management. There's one way, it's called TPU API. And we also have the GKE, which is majority of the TPU customers are using GKE to manage TPU for orchestration. With GKE, that's basically gearing towards the large-scale training and inference. So GKE will basically optimize for the good put, where it's focusing on the scheduling good put and the runtime good put. Scheduling good put is to basically enable fast to start the job, and then runtime good put is to enable all the resources be ready and prevent interruptions. So from the scheduling good put perspective, GKE is enabling largest clusters for 65K plus nodes with 250,000 chips for the GKE job to run a single training job. And then from the runtime good put perspective, we're also enabling fast container startup so that it can improve from 5 minutes to less than few seconds with preloading. We're also providing the high-scale checkpointing so that it can basically provide checkpointing once the job interrupted. You can quickly restart with the saved checkpoint states. And that can improve the good put by 6%.
Just a refresher, because this is the first time we've seen good put here today.
Yeah.
good put is a kind of a balanced
Yes, so
throughput measure.
exactly.
Yeah. Can you explain it a little bit?
Yeah,
for everybody?
yeah. Basically, MFU is usually what people think about the efficiency of the accelerator, and then, but it's not just about MFU. So we're basically adding the scheduling good put, as well as the runtime good put on top of the program good put. Program good put is essentially the traditional MFU, and then the automated hot swap with job set, that's also improving the good put by 45%. That's essentially what GKE can bring a lot of benefits, and many customers who are running large-scale training and inference, they are our GKE customers. Okay, I think I'm almost running out of time. Just want to bring inference is also a big focus for TPU, and we are providing various inference stack to our customers as well. So VLM, which is a well-known inference stack for TPU, so we're enabling it, and also JetStream, which is based on our JAX framework. So essentially, we want the customers to adopt TPU easily, and we're embracing the ecosystem for the customer to use our TPU.